Okay, I think we can start the webinar. Welcome everybody for the last webinar of the INN-PRESSME project. My name is Attila Uderski. I'm representing Leonardo Ltd within the INN-PRESSME project. It's a great pleasure to welcome everybody. We had a series of webinars throughout this relatively long project, and this has come to a conclusion with the final topic, which is focusing today on transport and consumer goods. The agenda looks as follows. So we will start with the presentation from STEM about the different services to support the upscaling, and some examples will be also mentioned from the automotive and sports goods sector, hopefully the good kind of experiences. Then we will follow with Fraunhofer ICT presentation about technical services for these very specific industries. And the final third presentation will be provided by ITB for the same kind of topic, what kind of services we can expect for such industries. Just some technical information for the participants that this meeting is being recorded. And if you will have any question, I would like to recommend to do it in the chat box so that after the three presentations, we will be able to respond or reflect to those specific remarks or questions from the attendees. So in order to start, I would like to ask first Ahmed El-Kassas from STEM to share his presentation and conclude with the sharing of this material. Thank you.
Okay. Good morning, everyone. Can you see my screen?
Yes, we can see your screen.
Can you see the presentation now?
Yes, presentation is very much visible. Thank you.
Okay, very good. So, good morning, everyone. I'm Ahmed El-Kassas. I'm going to be presenting INN-PRESSME services and SAP and INN-PRESSME marketplace. So, first of all, a quick introduction. What is INN-PRESSME? I know you must have read about it, but INN-PRESSME, in a nutshell, is an open innovation test bed that consists of state-of-the-art pilot lines. These pilot lines enable the development of new market-ready products and goods from bio-based sources. So, how do we enable that? How do we do that? So, we do that for the entities who want to develop these nanomaterials or bio-based materials. We guide you through every step of the development process, in which the first step, of course, is the interaction with the SEP, or the single entry point of INN-PRESSME, as an access point to all the pilot lines and services of INN-PRESSME, in which we guide you through the different stages of the process, starting from the formulation and processing of the materials to develop the end products, and also recycling the end products to produce reused materials, which enter the process again, finally developing the nano-enabled bio-based products, which we are aiming for. Moreover, through the interaction with the SEP, you can get access to the OITB assets, but also to top research centers, the open innovation ecosystem, technological partners for your projects, and even events that for your business that can help you in this development process. And of course, one of the ways to access the INN-PRESSME marketplace and interact with the SEP and the ecosystem is the digital platform, which I will make a quick demonstration about now. So that is the home of the platform, through which you can see the activity of your profile, some form of a feed for your activity. And through this, you can find the different pilot lines of INN-PRESSME. So you can see them in details, you know what are the services of them, what can you do through them, and everything in detail about them. And here is the documents part, which provides you with the documents that you would need within the process. So for example, in the meantime, we had, in this screenshot, we had the guide for applicants, how to do the application for the open call for INN-PRESSME, and so on. And any further documents that would be needed will also be there in the following process. And here is the events calendar that includes the different events happening in the open innovation ecosystem. And also you can add a certain event to your calendar, such as this one. And here, and this part so far was related to the open call applications, that's why it's called open calls, but it's going to be changed at the end of the project to customer proposals, in which the customers will contact the SAP to use the services of the Open Innovation Test Bed, which were provided in the pilot spot. And finally, there is the community part, which includes the different organizations in the ecosystem, which will enable the communication with the different stakeholders in this ecosystem. And basically, this sums up the platform. But the more important part is what are the services that INN-PRESSME provides. So these are the different pilot lines of INN-PRESSME, and let's start by the first one, which is the surface treatment concept pilot by VTT, which is coating and film preparation line with several coating units. And it provides various bio-based dispersions and polymers have been applied, and rod coating applicator on fiber-based substrates using this pilot line. And then the second pilot line is an additive manufacturing 3D printing pilot, which allows surface modification while printing, which allows increasing efficiency in processing of nano-enabled bio-based materials through additive manufacturing technologies. And then the pilot by CDTech for the production of electrodes for the optimization of the production of bio-based materials. And then the pilot by Fraunhofer, which is the foaming pilot line, which establishes a development environment for bio-based particle foams. And then the pilot by Fraunhofer IC for improving the quality of bio-based coatings and nanoparticle synthesis. And then another pilot by VTT for data mining as the basis for efficient production of flat scale polymers. And then the pilot by RISE with an increased level and optimized level of nanocellulose crystal production. And then another pilot by VTT, which is starting the efficient industrial use of cellulose nanofiber. And finally, the pilot line by CDTech for the production of novel cellulose-based bioinks and slurries. And this basically sums up the different pilot lines of INN-PRESSME. But now about the INN-PRESSME success stories. The first success story is in the automotive sector. So it started by like this part was usually produced from fossil-based sources, and we managed to produce it from bio-based sources. And first step there was the conversion stage to provide the micro nanofibrils, the flags, and then went to the step of formulation and optimization of the biopolymers with different loading fibers and the characterization of new materials, which went to the next step of processing the new materials to extrude the filaments to be used for 3D printing. In parallel, Fraunhofer developed the coating material, and the last step was to do the 3D printing using this coating material and the filaments that were extruded, the extrude filaments, which in the end gave us the required product for the automotive industry, in which our partner for the project was CRF. And then comes the second success story, which was for the development of inner shoe soles. And similarly, the first step was the conversion stage, providing the flags, which went to the step of formulation optimization of the biopolymers with different loadings of fibers and characterization of the new material. And then next to went to the step of processing the new materials to extrude the filaments that would be used for 3D printing. And in parallel, Fraunhofer developed the coating material. And the last step was to do the 3D printing using the coating materials and extrude filaments, which in the end gives us inner shoe soles from bio-based sources, which was our goal. And that would be the summing up for this. Thank you for your attention for this presentation.
Thank you very much, Ahmed. Again, if the participants will have any questions, let's answer them after all the presentation, and please insert your questions to the chat box of Zoom. So thank you very much. I think we can go on with the next presentation from Fraunhofer.
Yes, thank you very much. I will share my screen. Can you see my presentation now?
Yes.
Perfect. Thank you very much. Yes, welcome also from my side. My name is Christoph Mack, coming from Fraunhofer ICT, and I am presenting today the test case of the bio-based boxes and also the services that we offer in the Open Innovation Testbed. Looking at the agenda, I have two main topics. One is the presentation of the test case, so what we did in this development during the project. And the second one is the presentation of the services that we offer for industry with our foaming pilot line. Coming to the test case, the bio-based boxes, we had one overall aim, which was a socio-economical and ecological aim. The reduction of the CO2 footprint of materials, the increase of renewable resources, the avoidance of petrol-based materials, and in the end also increased recycling rates for biopolymers. What does that mean for our technical development? We wanted to find a bio-based substitute for expandable polystyrene, which has similar properties and can be used in packaging applications. In the end, expandable polystyrene is quite a high-performing material and used in a lot of applications, especially in packaging, like, for example, fish boxes, but also in building insulation or in more technical parts like bicycle helmets. To achieve that goal, we needed to optimize or further develop the bio-based foams that are already existing, especially with regards to temperature stability and mechanical properties, which in the end is also related to the fusion of the single beads of the foams. What was our approach? We used polylactic acid as a matrix material. This is one of the most available biopolymers worldwide. It's also one of the biopolymers, or the only one with a, I would say, close to reasonable price, especially with regards to the technical performance of the material. So we choose this material as a matrix. We developed lightweight expandable PLA foams to be able to use them in the existing processing infrastructure, which is there in the industry. We also developed 3D printed components to individualize packaging solutions. And in the end, we wanted to process everything together in a one-shot process to combine the foam together with the 3D printed parts. Coming to the partner structure of this test case, we had on one side the material providers with VTT, Ivnierz, who provided the fibers. Then we had CEA, who developed a recipe for the 3D printing filament, which was then produced by IPC, ITIP, who did the 3D printing, Fraunhofer, who did the bead foam development, and WSVK, who in the end was our industrial partner, who did the manufacturing of the demonstrator parts. When we come to the 3D printing, we used cellulose nanofiber reinforced PLA, which was provided by VTT and which was compounded by CEA. The filament was developed for the 3D printing, and in the end, those CNF reinforced filaments were printed to components. In this case, it was a data logger or a holder for a data logger, for example, to log or to track the temperature of such a inside of a thermal box. Coming to the bead foam development, which took mostly place at Fraunhofer ICT, we developed a special recipe made from PLA. We loaded this recipe with gas to receive gas, to receive expandable granules. Those were then pre-foamed and molded to a sample geometry, and then we did the characterization. And this was done several times, of course, in an iterative way to improve the properties. Here you can also see the single product throughout this processing chain. So we have the gas-loaded beads, which can be expanded like a little bit like popcorn in the end. Then we have the foamed beads, and these foamed beads are then molded together with steam to such a part. In the end, in this case, it's a sample geometry. Then we did the upscaling together with our industrial partner. So Fraunhofer provided the material, 5 recipes in total in a larger amount. So WSVK could produce on their demonstrator tool 55 sample in the end, which were then again analyzed to check which was the best of these recipes. And in the end, we achieved improved temperature stability and mechanical properties at the same time, which was also the goal of our development. And WSVK also made a quick video of this demonstrator production process, so you can get an impression on how that looks like. And so what do we have in the end? The final result of the test case is a non-petro-based packaging demonstrator made from close to 100% renewable resources. In this case, it's a lid of a thermal box made mostly from PLA, some fibers. And you also see here the data logger holder, which was 3D printed and incorporated during the production process. Coming now to the technical services for industry, which we as Fraunhofer ICT can provide. So we already before the project, we had an existing platform for development of bead foams along the whole processing chain. This was further upgraded during the process, so we can offer additional services now. What we can do is to really cover coming from the polymer to the final product. So material development, compounding, material pretreatment like coating or drying, then the gas loading, the pre-foaming, the molding, and also, of course, the characterization, which is always important for such a development in the end. Coming to the single process steps, to give you a little bit more insight on what can be done and also on what scale we are working on. So we have, for the bead foam extrusion, we have a Lie-Stritch twin screw extruder with a 27 millimeter screw and a throughput of up to 50 kilograms per hour, a Gala underwater pelletizer with up to 10 bars pressure, and we can dose various blowing agents, being CO2, nitrogen, pentane, propane, ethanol, so more or less all which is common in the foam industry. The throughput is enough to provide enough material also if you want to do like pre-series with your developments, or you have a material that you would like somehow to upscale. So here we can really provide hundreds of kilograms or even a few tons for your development. But also, of course, on the other side, also low amounts are possible, which are then also processed, for example, in our lab, like with our preforming unit, which is a small industrial scale preformer, suitable for all common and special materials. The highest pressure is up to 2.5 bars. And we also have a special setup for the pressure loading of the foam beads. Coming to the bead foam molding, we have two options here. We have an Allenbach steam chest molding machine, which is also small industrial scale. But we have one specialty here. We can go up to 7.5 bars in steam pressure. resulting in a wider processing window, and also enable the possibility to use materials which need higher temperature during processing. The second technology, which is the radio frequency molding, which is quite new, coming from company Kurz, is also available. In this case, it's more like a, I would say, pilot scale. Here, radio frequency is used instead of steam, and it works a little bit like a microwave in the end. And we can have molding temperatures of bigger than 240 degrees in the end. And this is also really broad processing window for polymers, which also may not be suitable in the steam chest molding process. Coming to the upgrades that were done during the project. So we developed a viscosimeter, which is installed now on the beadform extrusion line. It helps us to control the process and also to monitor the process, and resulting in a better quality control of the whole process. And also, of course, we can study the influence of blowing agents and additives on the melt properties. So viscosity always is a big factor, especially when blowing agents are added. You change the viscosity of the melt, and therefore you see really nicely and sensitive if there are changes in the process or in the dosing system. Another upgrade which was done during the project was the installation of drying units with conveyors as well. And also, what is the main part of this is a moisture surveillance sensor to check and to control the moisture of the polymers which have been dried before taking them into the compounding, because this is one of the, especially for biopolymers, one of the critical values you have, because degradation is taking place in the extrusion line if the material is too humid in the end. And then the last upgrade was a very, I would say, big one. So we installed a data acquisition and monitoring system along the whole processing chain of the particle foams to homogenize our process monitoring and also documentation. So we really can track now the materials from the delivery till the final product and during characterization. And we have like a tracking history with regards to process parameters, with regards to recipes, also additional values from the environment like temperature or pressure, which have been there. And therefore, we really can somehow target the developments much more, also with regards to data-driven analysis in the end. And just to show you a quick, one page of our system. So this is now the control system, which can be remotely accessed. So we see all values. This is an archive value, so not live in this case. So from a few days ago, we see all kinds of sensor values that have been measured of the melt pump, of the underwater pelletizer, the die plate, and we can see if there have been any anomalies. We can see if the values are in the desired range, set points to the value which actually exists, and this helps a lot in checking for process control and also in the analysis, in the later analysis of the samples. Coming to the conclusion. We successfully implemented the test case bio-based boxes. So you see a very nice demonstrator case in the end. Fraunhofer ICT offers services for the development, testing, upscaling, and processing of bead foams along the whole processing chain. And we have a very long-standing experience already in the development of thermoplastic foams, being bio-based material, which was very core of this project, but also other materials like petro-based or recyclate materials. Additionally, I want to say, but I think Marta will say a little bit more about ITIP services, but I also want to mention that ITIP offers as well services for 3D printing, and ITIP was also part of this test case. Thank you very much.
Thank you very much, Christoph, for the very interesting presentation. It was a very impressive user interface that you showed about the data control and monitoring, and also the video was very nice to see the result that actually can be taken to the hand. Okay, I think we can go on with the final presentation from ITIP. Marta, can you please share your screen?
Yes.
Thank you.
I'll do. Good morning, everyone. Let me share. I'm having some problems. Hang on. This one. It's not allowing me to. I think now you can see my emails. Can you see my presentation? Can you see my presentation?
No, we see your emails.
Still my emails. Okay.
Yeah.
I'm not sure why it doesn't show. I press share, but it doesn't show now. Now it does. My PowerPoint. Here it is. Can you see it now?
Yes, perfect.
Okay,
So but it's not
You can see the presentation now. It's perfect. Thank you.
Yeah, perfect. Thank you. Well, once again, good morning, everyone. I'm gonna be talking today, as already Christoph said, about the 3D printing we've been doing within INN-PRESSME. I'm going to present the two successful test cases that Ahmed mentioned in his presentation, and how we incorporated these bio-based polymers into the 3D printing. I'll just skip this. So the objective we had at ITIP and in general in our pilot line, together with the partners that I'll introduce you in a second, is how to use bioplastics and natural fibers to achieve bio-based materials that had specific properties and functionalities, that they had to be at least equal or even better than the fossil counterparts at competitive prices using 3D printing technology. Here you have all the partners that they have been involved. This is basically what Ahmed showed, but both slides together. So for the fibers, we had the partner IWN, who modified and provide us with the fibers. I'll explain you a little bit more what the process consisted of. Then we had the formulation, which for one test case, for test case 5, which is the automotive car part, was done by our partner CEA, and for the inner shoe soles, it was done by ITIP. Then our partner IPC, for both test cases, what they did is they transformed that.
Marta?
Sorry. Yes.
Interrupt you. I don't know. Are you changing slides? Because I don't.
Yes.
Does everybody see it, or is it just me locked on the?
No. Marta, can you put your screen into presentation mode and then?
It is in presentation mode.
Because it doesn't seem like if it is in present. But now it's skipped to the right slide. Yes.
Now it's slide 3.
It's slides.
Yeah, but it's not in presentation mode, isn't it?
No.
It's not in presentation mode, but at least we can see the slide.
Yeah, maybe you can customize the toolbar, then it's a little bit bigger.
Yes, I'll do that. I'll try to make it, as big as possible.
Yeah, it's good now as it is.
Yeah, okay. So I was explaining, I was explaining the partners involved. I was talking about IPC, who were involved in the part that what they did is transform the compound that CEA and IT produce with these bioplastics and fibers. They transform it into a filament that then could be used for 3D printing the end users pieces. That our end users were CRF and for the automotive part, and Productiva for the inner shoe sole. In parallel, as Ahmed mentioned, we had partner Fraunhofer, who developed a coating that gave these final pieces antibacterial properties, and in some cases some better behavior against, for example, the sun action in the car piece. The next slide, as I mentioned, it summarizes the process that our partner IWN had to prepare for the fibers to be added to the polymer matrix. The degamming was done to remove substances, so to be able to obtain micronized diameter of the fibers. The selenization was done to improve the addition between the fibers and the polymer matrices. The grinding, as its name says, is to carry up to the micronization of the length of the fibers, and the ringing, which was introduced a little bit later in the project, it was done to improve the efficiency of the microfibers purification. Once the fibers were ready, the next step was to introduce them in those matrices to produce the compound. For the automotive components, EA used polyamide 1010 with 5% of flax fibers. And for the personalized inner shoe soles, at IT we selected BioTPU with 5% of hemp fibers. This selection, you can see here, is just one line. It was a lot of iterations with different percentages, different types of biomaterials, but these are the ones that were selected after analyzing both the printability and also the mechanical properties of the materials. Once we had the compound, the filament was produced for then being able to transfer the material to the 3D printing process. Let me show you. Okay. So for the automotive parts, the process that I just explained until now, they are common for both test cases, but now I'll go into more detail for both of the test cases, starting with the automotive production. What we did is the aesthetical trim on the dashboard, the one you can see here on the left. That's the one we decided to print. Is on the driver's side. Nowadays, this air vent fascia is manufactured via injection molding using polycarbonate and ABS materials. But since the center style is often asking for a special series with an associated low volume production, the idea was to produce this trim by using additive manufacturing instead of, so it's a cheaper solution and it's a faster than having to produce a mold specifically for these short run pieces. Here you can see how some of the printing process went. We had to use, here I'm not the expert in 3D printing, it's my colleague Raquel who is traveling today, but the tree, you can see that tree building structure, that's the support because it's a very vertical piece, otherwise it will open, it will detach the layers, and that was a problem. There were a lot of trials to get these pieces printed. What we did, instead of printing a lot of demonstrators, because I just mentioned it was quite difficult, what we did is to print these squares that you can see here in the picture, and they were tested with and without the Ormoser coating developed by Fraunhofer, which confers antibacterial properties. The material, here you can see the list of the tests that were performed, and just in general, the material show good mechanical properties. This grade was identified amongst the others to have the best compromise in terms of physical and mechanical profile due to the characterization that was done previously. And also to mention that the cold impact and thermal cycles confirm this assumption. And considering the light aging, we can say that the coating, as I mentioned also previously, has proved that the material is better with this coating. It stands the aging through the lighting. It's better with this coating that Fraunhofer developed. For the personalized inner shoes, before fabricating the final demonstrator, that there's been a video around and there's been also some articles about it. Well, lots of different design iterations were necessary in order to achieve what the product required. It's something we need to work on, so it cannot be really hard, it cannot be very flexible, but it needs to hold the weight of the person. So a lot of tests and iterations in the design were performed. The initial, you can see there, it's very nice. You can see the inside of the structure of the inner shoe sole, but this initial lattice structure didn't provide adequate support, particularly on the heel area. So it resulted in instability walking. So what we did is, together with Productiva, decide that the entire shoe sole was joined together to prevent the formation of redundant walls generated by the fuse by the 3D printing method. This demonstrator was also coated with the biomaterials prepared by Fraunhofer. In order for the coating to give the bacterial properties and to attach properly to this sole, it was necessary to follow the steps that you can see in the picture, which was to apply a pretreatment of plasma. Then we spray coated following the directions provided by Fraunhofer, and then it needed that UV post-treatment to fix the coating and to let it dry and cure. Once we had the sole printed, the next step was to design the upper of the shoe sole, choosing the colors and the material. And what we decided is to go with 100% bio-based materials in order to make it a full eco-friendly model. And these are the pictures. This is the result of joining the inner shoe sole with the recycled materials. The validation of this demonstrator was carried out in four different individuals wearing 3 different types of shoe soles. The first one was a normal shoe sole without any personalized insole. Then a generic shoe with a personalized Productiva insole, and the third one, the one fully created in INN-PRESSME, the custom footwear. What was measured were the differences between the mean pressures, the maximum peaks of pressures, the total contact surface area, and also a lifetime test was carried out. It was in INN-PRESSME, the results that we could see for this testing is that this inner shoe sole reduces the maximum peak pressures and the mean pressures. And also the lifetime test, after applying more than 10,000 cycles of the metatarsal flexion, which is this movement that the foot does, it showed that the prototype had no permanent, it was not neither deformed or damaged, so it was considered to be appropriate for the market. So just concluding, the automotive parts has given a good and a positive confidence on the applicability of this biomaterial to produce short runs of interior automotive components. And for the personalized inner shoe sole, the material meets the specifications and the technical requirements of a specialized podiatrist. And it's, as I just mentioned, it's been observed that it meets the requirements of a therapeutic insole. It's demonstrated its resistance over a high number of cycles, indicating that it's durable. So just finalizing, I didn't include what the technical, what we can offer. But as I just mentioned in my first slide, IWN, I'll go back to that one, IWN can provide any type of micro or nanofibers. CNITIP can do, amongst many other things, can do the compounding, study how the materials behave. If it's possible to mix them, in which quantities. IPC is specialized. They got the Meteor special machine to do the filament at industrial scale. Then Fraunhofer, of course, has the registered Ormother mark to conquer this antimicrobial and other properties that improve the material. And at ITIP, we can do these biomaterial runs, 3D printing runs, which not all the machines in the market can work with biomaterials or with developed materials. Most of the really big industrial printers, they only allow to use their own materials that they sell, not an ad hoc material. But at ITIP, we can do it for material 6-7, and now we've got a new printer which will allow us to go to higher TRLs to industrial scale. That's what we can offer. Thank you.
Thank you very much, Marta, for this interesting presentation. It's good to see that the personalized inner shoe soles have been developed and people can wear it and actually use it for everyday purposes. This is really good. And I also understand that the upper part of the shoe has been also being provided from recyclable materials. So thank you very much for the presentation. I'm taking a look at the chat box or the Q&A. I think we have a comment there for seeing the prototype in live on YouTube. So if you feel like checking this first prototype on YouTube, you can go there. I'm also taking a look on the chat box, and I don't see any questions there. So maybe I will have a question to Fraunhofer. I remember from this video that there was this the cooling bag lids, right? That they look really good, and it's made of this foamed beads. Did Fraunhofer conclude any kind of investigation or research or background action to see what is the degradability of this foamed bead or biodegradability issues? Is there any actions took on that part?
Not yet, as it's a pure PLA, the foam, we assume that it has the same degradability like PLA itself. So that means we assume that it is industrial compostable. We are more focusing on the recycling of the materials to really retain the value of the material itself.
Okay, thank you very much. I know that this is a common problem everywhere, so yeah, that's good to know. Okay, again, let me see if there is any other questions from the participant in the chat or in the Q&A. Well, I don't see anything else, so I think then we can conclude this webinar today. Thank you very much for the presenters, for the participants as well. Please note that as this webinar was recorded, it will be available on the project website, INN-PRESSME.eu, in the coming days, hopefully. And I would also like to recommend to check the previous sessions, the previous webinar sessions. We had 3 more webinars throughout the lifetime of the project. Please check out that as well if you are interested. And I also could recommend the website as well to see if there is any new updates on the results of the project. So thank you very much for the participation, and I'm wishing you a very good day.
Thank you. You too.